Hello and welcome to the SimScale webinar, Pump Design Powered by the Cloud. I'm your host, David Vaughn. Just a reminder before we get started that all microphones will remain muted throughout the webinar. If you have any issues with audio or other technical difficulties in the webinar platform, please use the chat window to ask for assistance from our webinar administrator. So today we want to talk about pump design powered by the cloud. Looking at the registration list today, there's quite a few folks who will be joining the webinar that are not familiar with SimScale. So I want to give a brief introduction to SimScale for rotating machinery specifically and industrial equipment. And then we've got a big announcement to talk about. We're very excited. This is a big day in the life of SimScale, especially for these types of applications. And an awesome guest speaker lined up for you, Ben Walt from Hazleton Pumps. And they've got some really great information about both CFD simulation for pump design, as well as using the SimScale's structural simulation for troubleshooting field operations. It's a really good case study and story. Then we've got a live demonstration of that big announcement that I mentioned from my colleague Anirudh Uni, who will be joining us as well. And we will have a Q&A session at the end, so please, throughout the webinar, feel free to type your question into the questions panel of the GoToWebinar interface, and we'll go through those questions toward the end of today's presentations. Great, so I promise to be brief here, but again, I think it's important to kind of set the stage and provide a foundation for the story that Ben is going to tell of Hazleton's journey using simulation in the cloud. Earlier this year, SimScale announced that we are investing in and are committed to bringing cloud-native engineering simulation to the rotating machinery and industrial equipment market. That commitment is to first be true to our corporate purpose of making engineering simulation technically and economically accessible across the enterprise and throughout the product lifecycle. But we also understand that this industry has unique requirements for the accuracy and speed of simulations across a wide range of applications. So this is the commitment that we have made to the industry. The SimScale Cloud Native Engineering Platform is accessible through our browser-based web interface, as well as through partner integrations and/or custom integrations to further enable digital transformations. Users have access to our end-to-end simulation stack literally anytime, anywhere, and at any scale. Now, of course, economics play a huge role in making this technology truly accessible. It's not all about just the browser-based, cloud accessibility. Current, so let's say traditional simulation platforms and desktop applications, HPC applications require a huge investment or economic investment. So economics play a big role in making this truly accessible to the market, and we address this challenge by minimizing IT and licensing costs through usage-based pricing and automated HPC orchestration. Big part of our commitment to this industry has been an investment in proprietary simulation technology, specifically designed to provide fast and accurate results for rotating machinery applications. We have a number of companies that have taken us up on our offer to try SimScale's new technology for themselves, which has resulted in literally an onslaught of validation and benchmark cases from the industry, right, beyond academic cases. This includes our guest today, Hazleton Pumps, and as you'll see in Ben's presentation, the results have repeatedly proven these claims of accuracy and speed. He's going to give several of those comparisons himself. It's the same story, as I said, with the speed. The investment in this proprietary technology is paying huge dividends for our users. And it's not all about just the CFD solver technology. It's the entire package that includes robust and automated binary tree meshing, and it's truly the fastest solution on the market we believe, and have yet to be proven differently. And again, Ben will provide specific comparisons in his presentation. Besides the investment in CFD technology, SimScale is also investing in structural and thermal simulation technology to provide the ultimate versatility for all disciplines of rotating machinery and industrial equipment simulation. The Hazleton story provides a great case study, as I mentioned, in the need for this versatility to maximize the value of simulation throughout the product lifecycle. It's really a great case study in the use of engineering simulation for field operations and later stage product life cycle. So the big announcement, super excited. This is truly an innovative and unique solution. The ability to automate pump parametric studies, aka pump curves in this particular application. So as we've said, right, this new technology available in our cloud platform is we're able to very quickly provide accurate results for single simulations. But now, since we are orchestrating all of the HPC resources and doing everything in the cloud, we can now offer the full sweep of simulations to create a pump curve in the same amount of time it takes to run a single point. All of this is completely automated within the platform, easy to use user interface. Again, as far as I know personally, this is truly a unique solution. I don't know of anyone, any other platform that is able to provide this kind of accurate, fast, full pump curves in just a matter of minutes. So we're truly excited about it. Really invite all of you to try this for yourselves. We'll have more information about how to contact us and get a trial license at the end of the presentation. But this is just one of those things. I've been in this business a long time, and it's one of those things that you need to experience yourself. You need to do it yourself, and you'll be hooked. And as I said, we'll have a demonstration of that technology after we hear from our guest speaker. So it's my pleasure now to welcome to the stage Ben Walt, engineering manager at Hazleton Pumps. And again, I've seen obviously the presentation. I'm truly inspired by it. I love the multidisciplined approach to using cloud-based simulation. It's not just about CFD. It's not just about structures. It's not just about early stage design. It's truly making this type of technology simulation available throughout the product lifecycle. So Ben, I will turn over the presentation.
Thanks, David. Thanks for the awesome introduction. And hello to all the listeners. I think it's most definitely a very exciting time for SimScale. And what I really enjoyed from what David said is you kind of have to try it for yourself to kind of believe it. It's really interesting, like the first week, I was contacted by SimScale, and there were these specifications that were claimed, and I was sitting there in disbelief until I tried it for myself. It was just utterly mind-blowing. So anyways, to start things off, yeah, firstly, let me introduce Hazleton as a company. We have been in the pumping industry for about 40 years. We design, develop, and manufacture pumps in-house. We've been to mines, factories, and we've won numerous innovation awards from 2007 all the way up to 2018, and some in between as well. So we're very proud of that. Pumps is just what we do, and we've been doing that for quite some time. Just some background on myself. I started at Hazleton about a year ago as engineering manager. I've used several simulation programs in the past, which have made me quite familiar with packages like StarCCM, ANSYS, and OpenFOAM, etc. And it's quite specific experience in the fields of military vehicles and designing nuclear plants. And at Hazleton, we've been using open foam for the past year to simulate our pumps. About 6 weeks ago, we moved from open foam to SimScale, and which is quite a significant move for us internally, because we strongly and firmly believe in open source software, and it'll take a lot to convince us otherwise. But yeah, it happened, right? So yeah, next slide. So the agenda for me is just to quickly give some backgrounds on, the simulations that we did run and how we ran it. Also considering, how the new SimScale solver changed everything for us for rotating machinery. And I've got some results and comparisons that I would like to show you. And at the end of my slides, additional to this, there's also a vibrational analysis that we ran that really helped us a lot for solving an in-field problem that we had. So yeah, like I said, we've been running open foam for about a year. We acquired an expensive HPC at the time. And since then, we simulated 12 different pumps, and we produced more than 1 terabyte of simulation data doing that. And the simulations kind of showed it was about 2 to 10% accurate. And it's very model and mesh dependent. Open foam is prone to be quite sensitive to the boundary conditions and how you mesh and how your mesh is set up. Sometimes it will run well, and other times it will run but not run accurately, and other times it just won't run. And we averaged about 3 to 6 days to simulate one duty point using AMI. And those of you who are familiar with open foam, it's pimple foam, it's the transient analysis tool. And also, yeah, if you run the same using MRF equivalent called simple foam, it takes about 9 to 15 hours on this HPC to run one duty point. Okay, so yeah, so obviously to plot a pump curve, you need at least 3 points, and you actually ideally want 6 points or more. Okay, so, and sometimes generating that pump curve can take up to a month, right? So yeah, open foam. So yeah, if you're familiar with open foam, it's very tedious to set up your analysis. You have to prepare your geometry fully beforehand, and then you have to use something like Blender to create your regions, export that into your measure, view your measure in ParaView, and then eventually run it, right? And then you'll have some simulations that you can run and pictures that you can show, etc., etc. And we export this as a massive data file, right? So you've got, specific to pumps, we've got an array of data, and we're specifically focused on the Z moment of the impeller and also the pressure and flow rates that's produced through the pump. And it takes about half an hour to clean the data, just to clean the data and import it into Excel. And then you can start drawing your graphs and figuring out your efficiency, etc., etc. Okay, so enter SimScale, right? So for this, I prepared 3 case studies, and the one is developmental. Okay, so, and that's for the small pump, and there is actually 2 validation cases that we ran. Internally, it's really important for us to know, okay, if something's running fast, it has to run accurate, right? You can't sacrifice accuracy for speed. That doesn't make any sense at all. Okay, so we have these 3 pumps. The one is the first one that we did is a small pump, and I added into the list a medium-sized pump and a large-sized pump. The one pump in the simulation that we ran was actually weighing up to 9.5 tons, and the total length was 9 meters. That's the large pump to the right over there, and actually this same pump is the one that we did a vibrational analysis on. So the entire pump, the entire assembly, we loaded into SimScale for a vibrational analysis as well, but I'll touch on that a bit later. Okay, so first of all, we loaded this 5.5 kilowatt submersible pump into SimScale, and the idea was to do development on this pump. So we wanted to establish a baseline for the new impeller that we developed, and then possibly see how we can improve that impeller, right? So we uploaded the geometry, we extracted the water volume and ran the simulation, right? And now remembering open foam can take up to 6 days to generate 1 point. We were able to produce an entire pump curve in 7 minutes. So that is a 99.9% reduction in time. Actually, it's so vast that, I have to explain to our director, why open foam took so long. It's one of those things that you have to kind of think about how to explain your case now, right? So this is awesome because it really changes the turnaround time for doing designs. When you do a design, you have to analyze it. You have to look at where there are potential issues in the design, and then you have to reiterate, right? And that's how you improve it systematically. And working with 7 minutes to solve a case really expedites the turnaround time to do development. It is actually quite ridiculous. So at this point, we decided, okay, let's see how accurate the data is, right? So we go on to our second pump, which is the medium-sized pump that we did. The photo on the left is just basically a picture where we were at the test facility, our local test facility that we own. And the 2 images on the right are just the certificates, right? So don't worry too much about that. That's just to show that there is a certificate and we did test it, and we have the data to prove that. Okay, so we ran the same pump and we plotted the data, and we saw that for some of the data points, it looked like the same line. Okay, so the crazy thing over here is you expect about 2 to 3% difference because you have to allow for manufacturing differences. So manufacturing processes always deviate slightly from the theoretical model. So we expect about 2 to 3% difference. This is a special case. We did correct for head loss that we see in the pipes. So that just adjusts the orange line upwards by 5 meters head. And typically that's what we do for our local test facility because we know that's the inherent losses in the pipe. And we ended up with a curve that's almost smack on it, okay, which is pretty intense. And I also made a little simulation there to the right to show that, yeah, we simulated the inlet, the impeller, the volute, the discharge, and the top discharge head that goes out into the test facility. Okay, pump number 3, this is the big guy. Okay, so there's also, this one was actually tested at South African Bureau of Standards. We don't have the facility to run a pump this large locally. So the photo that you see there to the left is a motor that we attach to the top side of the pump that you can see there inside the red block. What you're looking at is actually the red block in the small model there. The top side of the pump, and then you can see there's electrical motor with a V-belt running it. The design power for this pump is actually 600 kilowatts, but we were doing a 250 kilowatts load on it at that time. And we have all of the data there to the right that's signed off and certified by the facility. And yeah, we also plotted the simulation results with what we found from SABS, and we found that we were plus minus 3% within that target. So I want to also kind of stress on this point that just to take the pump to SABS to test it costs about $3,000 per test. Okay, and if the test results are this accurate, we can do much of that work now locally rather, as opposed to designing, testing, and spending loads of money doing that. This case in specific took about 23 minutes to run, so it's a much larger pump, so much more cells, larger domain, and yeah, to be completely honest, the geometry isn't, as you can see to the right there, is not entirely cleaned for CFD. So basically what I did was I took the assembly, which is really loaded with lots of detail. I closed the gaps, loaded it into SimScale, extracted the fluid volume, and it takes about 4 clicks. And then I have the fluid volume, which isn't, it's not been cleaned, it's quite nasty. And I just throw it into the solver and ran it. And despite that, it still only took 23 minutes to run. And the thing is, my time is worth more than the PC's time. So, it's really a win-win for us, because it just goes to show you how robust the software is. To conclude, the fluid dynamic side of this new solver is basically we're moving from OpenFOAM to SimScale, causes us to reduce our simulation time from 1 month to about plus or minus 20 minutes, okay, to generate the entire pump curve. We eliminate HPC costs. So it depends on what you want to get, right? If you want to go all out, you can get something really expensive. In our case, we spent about $6,000 for a good HPC, and we don't have to worry about that anymore. And also, as I mentioned earlier, we have about 1 terabyte of simulation data just from 12 pumps. And managing that data is a yearly cost because we have to back up to the cloud, etc. And that comes down to 0. And then finally on the right, we actually found that the accuracy is equal to or better than OpenFOAM. Now, I'm not saying OpenFOAM is not an accurate tool. It's mostly because OpenFOAM is quite sensitive and it's case dependent. If you don't get the mesh right, if you don't get your boundary conditions exactly right, it's going to be temperamental. So it's also very accurate, but in general, SimScale is just really robust. I threw nasty CAD models at it, and it just spat out really accurate results, which is really impressive. Okay, so just moving on to the vibrational analysis on the large pump that we did. This is something that I just quickly wanted to touch on, and I have to give kudos to SimScale, is that we had this large pump installed on site. You can see that to the right, there's some clamps that's on the mounting plate of the motor. And they actually had to put that on because there were some local vibrations coming off the pump, which is really bad. It was dangerous. And, the people that were working on site were telling us, okay, there could be damage or failure. So, all of the red lights went off and the cavalry was called in, the cavalry as in consulting engineers and specialists, etc. And a report was issued to really change almost everything on the pump. We had to reinforce the motor mounting bracket, adding half a ton of steel. We had to add expensive structural members into the cradle of the pump. There was recommendations to change all of the bearings, etc., and it would cost more or less $40,000 per pump, and there are 5 pumps to change all of this, right? So it's really, really expensive and hefty design changes. Okay, so I pulled this model into SimScale. I had to mesh the entire model and all of the bits and pieces. SimScale support really helped me a lot with that. They did about maybe 70% of the work because most of the work is actually in the pre-processing of this. And we ran it. And if you look at the eigenmodes at number 6, which is the eigenfrequency of 13 Hertz, it showed a critical frequency of about 13 Hertz, which is at 780 RPM, right? And that means that 80%, and it also showed that 80% of the pump mass was responding to that critical frequency. And that's 20 RPMs away of what we measured on site, right? So really, really accurate. And we were able to conclude that, okay, don't run the pump far below operational speed. Operational speed was 1150 RPM. Don't run it too low because you're going to run into problems. And yeah, there's also some elegant and much more cost-effective mechanical upgrades that we could make that would obviously treat this issue. And yeah, I can't share too much about the case because it's still ongoing. But this simulation really helped us a lot. And I actually made a little animation for you guys to see how the pump was vibrating. So you guys can see here on this page Basically what happened is that your impeller and your shaft was basically stationary, and it was constrained that way because the bushings are soft Vesconite and high tolerances, so it's not actually keeping the shaft and the impeller where it is. It's just to give some balance, right? So the real structural side is on top, and you could see how that was just swaying and causing us massive issues. And we came up with a really simple solution to stabilize this 9.5 ton pump and just solve the whole issue, because without the simulation we wouldn't know what was happening, to be honest. And yeah, that's basically it. I can't speak more highly of the SimScale simulation software. I am an avid believer in open source, but this just blew me over. So I would like to thank you guys for your time and your consideration. And I think Anirudh is going to do a live demo, but yeah, over to David in the meantime. Thanks.
Thank you, Ben. Really appreciate you sharing that story with us, or those different stories. Again, you know, the multiple disciplines, being able to do structural and CFD simulation from the same, you know, cloud native platform, and the accuracy and the speed in which you're able to accomplish that. And kudos to you also for, you know, being willing to look outside the box a little bit and find the right solution for you. So appreciate you sharing that story.
All right, perfect. So I'm going to give you a live demonstration of the new pump curves feature. And this is something that I'm personally very, very excited about. One might even say very pumped, because this is really a game changer. So the plan is I'm going to show you a case with a centrifugal pump on it. So we've got experimental data for this pump. I'm going to set it up live from scratch, set off a bunch of simulations, get the pump curve, and then we look at the results. So I don't want to spend too much time on the slides. Let's just jump on into the platform. So if you haven't seen it before, this is the SimScale platform, and we are in the workbench right now. So the first thing to note is that SimScale is completely cloud-based, right? As you can see from the URL in my browser, all you need to do is go to simscale.com, log in with your ID and password, and everything you need to run your simulations is right there. So it's just like your Netflix account, where you just log in with your ID password. All your simulations, just like your movie titles, are right there when you need them. So the example I have here is the centrifugal pump that I mentioned here. So I've got the geometry with the fluid region, and I've also got a cylindrical body around my blades to model the rotation. So step one of setting up any simulation is just getting the CAD, right? So on the top left, this is where you can upload different CAD models, and you can upload as many different designs as you want in one go from pretty much any CAD tool out there, just by dragging and dropping it here. Now, once I have the CAD, the setup of the simulation is really straightforward. So I'm just going to hit create simulation, and this is where I get to choose from all the different types of physics that SimScale has to offer. So like we said earlier, it's not just flow analysis, but you can also do thermal analysis, or even structural and frequency or harmonic analysis like Ben showed. But for this demonstration, I'm going to use our new really fast and accurate subsonic solver type. So once I have that selected, I can create a new simulation just by hitting the button here. And under my simulation tree, I get a new simulation called Subsonic 4. So the setup is really straightforward, because you get a pre-populated simulation tree, and the workflow is really linear. So you want to go top to bottom, and you want to get a green checkbox everywhere. So the software is really smart. It's not going to let you run a simulation unless it has everything it needs, and it's going to tell you what it needs exactly by showing you these red circles. So for this simulation, let me just rename this to live demo so that we can keep track of it that way. And I'll start with the setup. So going top to bottom, the first thing is just adding the material properties. So you can just choose from our library. And in this case, it's just a simple water centrifugal pump. So I can just select that and hit OK. Step 2 is specifying the inlets and outlets. So that's pretty straightforward as well. So for the inlet, I can just specify a pressure. And for the outlet, I can specify a flow rate. But now this is where things start to get interesting, right? Traditionally, I could only specify let's say 1 flow rate at a time and run a simulation. But now we have this new parametric studies feature. So I can just click on this button here and import a table, and that way I can run all the flow rates at one go. So I can start typing out a bunch of flow rates. So as Ben mentioned, we need maybe 6 points for a pump curve, so I can start typing them out. Alternatively, you can also just upload an Excel sheet with those values, so you don't have to type them out manually. You can just browse for an Excel sheet and upload those 6 points. So I'll just add one more and maybe a 7th point for good luck. So right, I've got my 7 flow rates and I'm just gonna hit apply. Step 3 is determining the kind of results that you want. So to be able to get a pump curve, you want to look at a few things, right? So you want to be able to get the input power for the pump, and you can do that by creating a forces and moments report and selecting the impeller blades. The other thing we need for a pump curve is the pressure differential across your system, or the pressure head, and you can just create another report for that and just select the inlet and outlet phase. Now, the last step for setting up the simulation is just defining the rotation. And I can do that using the MRF, or multiple reference frames approach, or the frozen rotor approach. So I just need to select that body there, assign a rotation speed, and just make sure that my axis of rotation is correct. So as you can see in my simulation tree, I've got green checkboxes everywhere, and I'm good to start a simulation. So I'm gonna, instead of starting a simulation now, I'm actually starting an experiment with all these different flow rates. So I'm gonna call this my live demo simulation, and I'm gonna hit start. Now this is where SimScale is very different. So if you had a traditional tool or OpenFOAM, the reason it would take you so long to get a pump curve, like Ben explained, is you have to do 1 point at a time, right? You have to run one flow rate, wait for it to finish, do a second one in serial. But right now, as you can see, all those different flow rates that I specified are running in parallel on virtual machines in the cloud. So all the heavy lifting, the meshing, getting the results, all that is offloaded to the cloud, and none of that is being used from my local workstation. So I don't have to, pray that the simulation doesn't crash or leave a sticky note on my desktop praying that nobody touches this. I'm actually free now to do anything I want. So I could go and pre-process another simulation or post-process a different one. So in this case, let's say I want to run a different fluid, right? So I could just go to my material properties here and edit these. So let's say I want to see how this pump would fare with some kind of oil in it. So I'll just change the density and viscosity a little bit over here, edit those properties, hit OK, and start a new experiment and get a pump curve for this particular material. So I'm just going to call this experiment 2 oil and hit go. And now this sets off a whole bunch of other simulations on virtual machines in the cloud. So as you can see, you have access to virtually an infinite amount of compute power in your fingertips, right? If you want to do a different rotational speed, you can follow the exact same process and set up that simulation as well. So while this is running in the cloud, let's go take a look at the results of a completed simulation so that I can show you the kind of design insights you can get by running this on SimScale. So this is the exact same pump, but now we're looking at the results of the completed simulation. So you can see with this animation, I can visualize how the fluid or the water is coming into the pumps, how it's hitting the impeller blades and being pushed out wide due to the centrifugal forces, and I can see how it's going out to the outlet. So let me pause the animation and visualize the flow a little bit better with particle traces or streamlines. So with this, you get a really good qualitative understanding of some of the larger flow features in your domain. So I can see the flow around my blades. That all looks okay, but what stands out to me is more the flow around the outlet section. So ideally, I want the flow at the outlet to be as clean and straight as possible to minimize any losses. But I can see that there's a bit of a swirl component imparted to it here, right? Any unnecessary energy I'm imparting to the fluid as a waste, and that's reducing my efficiency, reducing my efficiency. So I can see a little bit of that at the outlet. So I want to investigate this problem a little bit more. And for that, I can start slicing and dicing the model. So the first thing I'd like to do is just visualize the results on a plane. And now we're looking at velocity, and these arrows tell us the direction as well as the magnitude of the flow, right? And this sort of highlights the problem a little bit more. I can kind of see that because of the small radius here, there's a lot of blue or low velocity flow that develops right next to it. And if I see the arrows here, they're not as nice and level and clean as I would like them to be, right? I can verify this a little bit more just by sliding this up and down a little, and I can see the problem here. So for my next design, I'd probably just maybe increase this radius a little bit more and try and get slightly smoother flow at the outlet. So this is just an example of one design insight you can draw by taking a look at these results. Of course, there's a lot more you can do with SimScale. You can look at things like where identifying areas of low pressure to see if there's cavitation risk, etc. But I don't want to show you all of that right now, because if I go back to my original experiment that I have set up, I can see that most of the simulations are already complete, right? So this is another great benefit of the solver, is that it is extremely fast. So you cut down your simulation time from days or weeks down to minutes. And as you can see with this live demo experiment that I set off using the default mesh settings, it just took 3 minutes. So if I go to my results now, you will see that I have a completed pump curve. So if I hover over to the pressure difference, you can see all 7 operating points, the flow rate at the bottom, as well as the pressure difference. And the same thing goes for the impeller forces as well. So I'd actually ran this simulation beforehand, took this data and put it in an Excel sheet. So it's very easy to just download this stuff and post-process even more. And I tried to compare it with the experimental data that we have. So for this particular run, we have 3 points of experimental data. And as you can see, for the input power, we're pretty much bang on within 1%. And for the pressure head, again, we're within 2% for the pump curve. So not only is it extremely fast, but it's also really, really accurate. So as far as a quick overview of the new pump feature, I think that's pretty much it from my side. I hope I've been able to demonstrate, firstly, how easy it is to access. So I'm doing this simulation, from a $300 laptop in my bedroom, and I'm extracting pump curves in minutes, which is pretty much unheard of. I hope I've been able to show you how easy it is to set up. So it only takes a few clicks and it's highly automated, and also how fast and accurate the results are. Right, that's pretty much it from my side, David. Thank you.
Great, Anirudh, thanks a lot. Really well done. So we've got several questions. I want to encourage, if those of you who have some questions, please type them into the question panel of the GoToWebinar interface. So have a few here for you. There was a question, I think, that looks like they found the answer, but I think it's worth talking about a little bit, Anirudh, about the defining units when you set up your boundary conditions and input conditions. Can you talk to that just a second?
You mean the different units that are available?
Right.
Yep, absolutely. So with SimScale, it's really easy to change the units. You don't have to work with metric units like I do. So if I go to my, let's say, pressure boundary conditions, I can just navigate on the toggle and choose from a whole variety of units. The same thing goes for the result, right? On the legend, let's say I'm visualizing velocity, I don't have to choose meters per second. I can choose a different unit like miles per hour or feet per second that I'm more comfortable with.
So there's a lot of flexibility built in.
Yes, precisely.
Great. There's a question about the general application of these parametric studies I wanted to address. So the question was, the specific question was about, can you create power curves related to wind turbines or other applications? So this is obviously a huge differentiator for the SimScale platform compared to competitors. So it's something that we really intend on driving and continuing to enhance to do parametric studies, of all different sorts, right? The first implementation is specifically for these kind of rotating machinery cases, the pump curve. So this is the first implementation. You'll see as new releases come out on a very regular basis, by the way. You don't have to wait 6 months. New releases, new technology, new capabilities, features, functions are released continuously, pretty much on the because it's a cloud-based platform. So the answer is all of that coming soon, and look forward to providing more of this capability in the parametric studies type of applications. All right, so okay, we can go ahead and address this one about the mesh and Y+ values and stuff like that. This is I mean, I can't overstate it. Now, to say it's a big part is an understatement, right? This is that at the heart of that proprietary technology that we've invested in, that you don't have to worry about that anymore. And I know I've been doing CFD for 20 years, and I know how hard that is to take, trust me. But it's true, right? That this is about making accurate simulation accessible across the enterprise. So there will always be a need for simulation experts to do, the Hero Mountain cases for validation of the most minute details. But really what we're about is making, good, solid, accurate, fast simulation available across the enterprise, right? For users around the world, for users in different departments, different disciplines, whether it's structural, whether it's fluids. And this proprietary technology that we've invested in allows just that, where you don't have to worry about that Y+. The meshing is automated. Of course, you have controls, right? And you'll need from time to time, case dependent, to update the mesh refinement. But the boundary treatments and wall functions are completely automated and very finely tuned for these types of applications. So again, I'm gonna just say try it. I'm just gonna say try it, like Ben did, and you kind of heard what he said, that he had to concede. Great. Sorry to get on a soapbox there, but that's exactly what the message that we're trying to get across. So great. Let's see, I'm looking at the questions here. We addressed most of these. So actually, maybe it is worth talking about. Ben, there was a question to you about using surrogate models. I'll let you answer it for yourself, and I have some thoughts on that as well, but using surrogate models to replace some, if not all, of the CFD.
So is the question that will we consider to do that?
Yeah.
Yeah, I think in context of our testing that we used to do quite often on site, we will minimize that to a large extent, and we'll obviously still test some of the more niche products that we develop and build. But yeah, if we're gonna have this new software, we don't have to run OpenFOAM anymore. It's kind of pointless. I mean, we can do some other funny simulations if we don't want to do like pressure losses in a pipe or whatever. But having the software now reduces the amount of dependency we have on OpenFOAM. And I love OpenFOAM, but it's a love and hate relationship.
Yeah.
So it was, yeah. So having SimScale really reduces the our dependency on OpenFOAM, and also our dependency on doing tests, because Test facilities are always kind of booked, so you have to wait a while to get a spot. And if something goes wrong on the test day, it just costs time and money and so on. So that'll significantly reduce the amount of testing that we'll do. We will never be able to move away from it completely. But that's the one thing. And also the open firm stuff is now up. We have a very expensive HPC PC just standing there, and it's just collecting dust. Actually, it's playing Spotify for me in the day, and that's what it's doing now. I mean, it's funny. I didn't think that would happen, but yeah, it's really exciting. It's it can't be overstated. Just can't be. It's something that you have to do for yourself because it's really fantastic.
Right. Yeah, for sure. Yeah, I wanted to address this a little bit too, because if you remember, I described access to the platform, right? So there's the web interface that Anirudh just demonstrated, right? So accessing the platform and the technology through a web interface, but there's also the API interface, which is being used quite a bit these days to integrate SimScale's simulation capability within AI platforms and machine learning and doing optimization type studies and developing neural networks. So I think there's obviously a long way we can go with that, and the future looks very bright there. I'll say though, for these specific applications, like for the Hazleton cases specifically, pumps, why do you need a surrogate model when you get the results in 3 minutes, 7 minutes, 15 minutes? It's kind of you've got the unlimited cloud platform, cloud resources. So for cases that require more computational resources, more time, then it absolutely makes sense, and we're working toward that. But for a lot of the cases, in this particular market, for pumps, fans, blowers, and those applications, right? It's almost not really necessary. You can just run the simulations directly, and you get more accurate results that way, and really almost just as fast as surrogate models.
Exactly.
So we're kind of at our time right now, and I want to make sure that we'll address any further questions one-on-one if we need to, or perhaps provide answers to the questions in a blog of some sort. At any rate, we'll get those questions answered for you. I want to thank Ben once more for coming on. Thank Hazleton Pumps for allowing Ben to come on and tell this story. I think it's really important for the market. And thank you, Anirudh, for your demo. And thanks again to all of our attendees as well for taking your time to join us today. I want to invite everyone, as I said, first explore, just get on the website and explore. There's plenty of on-demand resources at simscale.com where you can see recordings like this webinar will be provided there. And learn more. Let's get together and we're happy to do a one-on-one demo, benchmark cases if we need to. And most of all, like I've said several times already, try it. Just try it. One thing I want to say about that is, SimScale is famous for its community platform. We're providing access to some of the open source technology. This proprietary technology is not available on the community platform. So if you want to try this technology, these solutions that Anirudh demonstrated and that Ben has been talking about, you need to request a trial license. You can contact us directly at sales@simscale.com in order to get that trial license. And again, I encourage everyone to try it. With that, I will say thanks once again to all of you, and I hope you have a good rest of the day. We'll see you at our next SimScale webinar.